molten hot. And the sun only came later. Why did God do that? So we wouldn't worship the sun? God is the giver of... People say, where did the light come from? Well, God supplies the light in the new heaven and the new earth. Why couldn't he supply it at the first heaven and first earth? And then the sun was made to take over bearing that light. Well, it's also assumed that radioactive dating works accurately, which is what I want to focus on for the next half hour or so. So how do these methods work? Now, don't get bogged down with too many of the technical details because I'm going to try and simplify this as much as possible. But some elements, some atoms of some elements, for example, carbon-14 and uranium-238, have too many particles in their nuclei, so they are unstable atoms. And so those unstable nuclei spit out or eject subatomic particles to make the nuclei smaller and therefore more stable. So, for example, carbon comes as carbon-12, carbon-13 and carbon-14. It's all carbon. It's the same carbon as most of its regular carbon-12, but some atoms of carbon have an extra neutron in their nucleus, so they're carbon-13. Carbon-14 has 2 extra neutrons, so it's unstable, and it spits one out, and it decays. And that's what it's based on. This radioactive decay process is when these decaying atoms, that are known as radioactive isotopes, or radioisotopes for short, and one element decays into... From unstable atoms of one element decays into stable atoms of a different element. And the decaying radioactive atoms or radioisotopes are called parent atoms, and the resultant stable atoms are called daughter atoms. I'm just giving you some of the terminology. Now, minerals, rocks and fossils contain some of these radioactive parent atoms and the daughter atoms. Now, the methods that you've probably heard about are carbon-14. A lot of people think that carbon-14 is used to date rocks that's millions of years old. Well, I've got news for you. Most rocks don't have carbon in them. And carbon-14 decays so rapidly that if every atom in the Earth was carbon-14, all gone within 1 million years, which is why they don't normally date fossils with radiocarbon, because they already believe they're millions of years old. But that's a whole different story. We want to focus on uranium that decays to lead, and there's 2 types of uranium that decays to 2 types of lead. Potassium decays to argon, rubidium decays to strontium, and samarium decays to neodymium. And you might not have heard of those last 2, but neodymium is very strategic metal. You know those wind towers that generate electricity? The magnets in those have got neodymium in them that give them better... make the magnets better and give better production of electricity. So it's a very sought-after metal, but it's a rare metal, and so it's very expensive. So let's think about this process. What happens? A rock is chemically tested for these parent and daughter atoms. You collect the samples, you do a chemical analysis, and here's how it works. You've got the parent and daughter atoms that you've measured. If the decay rate has made constant, you can calculate how long it took for those daughter atoms to have come from decay of parent atoms. And if that period of time is then regarded as the rock's age. Well, I probably lost half of you, so let me try and explain it again like this. You're familiar with an hourglass clock, an egg timer. Or an hourglass was rated at 1 hour, because if you started with all the sand grains in the top glass bowl, it took 1 hour for the grains to fall to the bottom. Well, let's use this analogy. The top grains, we'll make them red, and we'll call those the parent atoms. And as they fall, it's analogous to radioactive dating, they turn into green sand grains at the bottom, the daughter atoms. Now, it's quite simple. Ladies, you're doing some baking in the kitchen, and you've put a cake in the oven, and you want to go and do some washing in the laundry, so you put your hourglass clock on, you started with all the sand grains in the top, you go out to the laundry, do your washing, you come back, and you want to know how long your cake has been in the oven. Well, you look at your clock, and you do a chemical analysis. You say, how many grains are up the top, how many grains are down the bottom? Well, you discover that half the sand grains that were at the top are now down at the bottom. So how long were you out of the room? Half an hour. And that's how simple it is. The geologists want to study how many red atoms and green atoms, and then because of the number of green atoms, they know how long it takes them to form from red atoms. They back calculate. So if we start with all the sand grains in the top bowl, it takes 1 hour for all the red sand grains to fall the bottom to become green sand grains. So a rock is chemically tested to measure the amounts of red and green atoms. And then we can, if the rate of radioactive decay or falling has remained constant at today's measured rate, then it can be calculated how long it has taken the measured amount of green atoms to accumulate from the parent red atoms. And that time period is regarded as the rock's age. Is your mind starting to think about this? What are the assumptions involved? What's going on here? The point is, there are 3 assumptions that you make with that hourglass clock. And if they're crucial for the working of that hourglass clock, they're even more crucial for the radioactive dating methods of rocks. The reason, of course, is that you were there when the clock started. And that's the first assumption. The geologists have to assume the amounts of parent and daughter atoms at the beginning when the rock formed. That is, the initial conditions must be known. You see, you have to assume there were no green atoms in the bottom of the glass bowl at the beginning. You were there in the kitchen, but guess what? The scientists weren't there when the rocks formed. How do they know that there weren't daughter atoms in the rock when the rock formed? They weren't there. They don't know. It requires an observer. So that's a problem, as I'll show you by practical examples in a moment. That's assumption number 1. Requires an observer, but it's about the past. They weren't there. Number 2, all the daughter atoms measured today must be only have been derived by in situ radioactive decay of parent atoms. You had to have a closed system. In other words, all the green atoms must have been derived from the falling of red atoms only, that is, there's been no contamination. This also requires an observer. Ladies, when you were out of the kitchen, you know what happened? You didn't realise it, but your mischievous 10-year-old son snuck in, lifted up the lid and put some more red atoms in, so that when you came in, you thought that was half and half, but you were wrong because he added more at the top. And now you were out of the room actually for 40 minutes and your cake's now burnt in the oven. You get the point? If you're not there to observe it all the time, how do you know there hasn't been some contamination? And if you weren't there when the clock was started, if you just walked into the room and you saw that hourglass on the bench and you saw the green atoms, you might assume that there were none there to begin with, but guess what? It just started. There were already green atoms to begin with. How do you know if it requires an observer? And then assumption number 3, the radioactive decay rate must have been constant at today's measured rate. But have the scientists been there for millions of years measuring these decay rates? No. We measure the rate today and we extrapolate backwards. We make a huge assumption that, and I'll show you in a moment, that we've only been measuring these decay rates over the last 70 or 80 years. So we take 70 to 80 years of measurements and extrapolate that back 4.5 billion years. That's 5 orders of magnitude extrapolation. And it should be readily recognised that there are problems with these assumptions. So the assumption number 1, there's no initial inheritance. In other words, no daughter of green atoms to begin with. No other processes affected the parent-daughter relationship. That means no contamination. And assumption number 3, constant decay rates. There can't have been changes. You should already recognise that none of these assumptions are provable. Why? Because the scientists weren't there in the past to observe and measure and test. The reason why they accept these methods is because they work to give them the millions of years. But in reality, not only are these assumptions not provable, they're not even reasonable. Because all 3 assumptions have been repeatedly falsified. And I did a study a number of years ago where I went into the literature, and in the textbooks even that are used in the universities, they document out of the literature the problems with these methods in terms of the assumptions that have been falsified. And I'll give you a few examples. See, daughter atoms have been known to have been inherited when rocks form. But even when not detected, it doesn't mean there hasn't been inheritance. Just because we make the assumption doesn't mean that there hasn't been a problem. Assumption number one is often violated, no inheritance. Subsequent contamination is common. You realise that if you may not have been down a mine shaft, but you can go down a kilometre down into a mine and you will still see contamination of the rocks. Down cracks, the water will come, bringing oxygen in the groundwater, and you'll see rusting at that sort of depth. And yet the samples are collected at the Earth's surface where rainfall, groundwater, atmosphere is readily going to contaminate. Uranium is very soluble in groundwaters. It will move in and out of rocks very rapidly. And so contamination is a constant problem. And even if it isn't detected, doesn't mean that it isn't present. So assumption number two, no contamination is often violated. And several lines of evidence have demonstrated conclusively that decay rates were grossly accelerated during a recent past catastrophic event. I'm going to touch on that again in a moment. So assumption number three, no changed rates, is violated by demonstrated past accelerated radioactive decay rates. Now I want you to understand the quality of the chemical analyses of the rocks is not disputed. The reason is that you can repeat those analyses. I can send pieces of the same sample to 5 different laboratories, and I'll guarantee you they'll all come in close to the mark, on the same mark. So, you know, they spend millions of dollars building these laboratories to measure such tiny amounts, and they do it very accurately. That's not the issue. The issue is the interpretation of those chemical analyses. I send a sample to the lab, they'll send me back the analysis, and then they plug the analysis into equations with the assumptions built in to calculate the age of the rock. So it's the interpretation of the millions of years based on these 3 unprovable, repeatedly falsified assumptions that we're disputing. So let me give you some concrete examples. Some of you, for this, may be revision, but that's fine. Mount St. Helens, when it erupted in 1980, after that eruption, a new lava dome started to build inside the blown-out crater. And we could actually observe these form. And my friend and colleague Steve Austin went up and got some samples from lavas in the lava dome whose age we knew by observation. We knew that the lavas had formed, had flowed out of the volcano, the molten rock had crystallized and cooled back in 1986. And in 1996, the samples went to the laboratory. So the rock from observation was only 10 years old. So what results were obtained? Potassium argon ages range from the whole rock at 0.35 million years up to one of the minerals, pyroxene, gave an age of 2.8 million years. That's one of the minerals in the rock that was separated. Why did it give such large ages? Simply because it inherited daughter argon to begin with. What do I mean by that? Well, most people don't realise that more than 70% of what comes out of a volcano is actually steam and gases. And in those gases is argon. So what happened is when the rock cooled and crystallised, it trapped some of that argon in the rock, and it didn't come from radioactive decay of potassium. But when they analysed it and calculated the age was based on assuming that all the argon had come from potassium decay. You get the point? The rock was artificially old because it was contaminated or inherited argon, the green atoms, the daughter atoms, to begin with. Now, this is well known in the scientific literature. Here's a list of examples came straight out of the scientific literature. Lava flows in Hawaii from 1800 to 1801 gave potassium argon ages of up to 1.6 million years. In Mount Etna, and in California and Arizona, again, and these are just several examples from the literature. I could give you screeds of articles from the scientific literature that document this problem. So you see, it begs the question, if a recent lava flow, a recent eruption, a recent lava flow, where we know the true age of the rock from observation or historical evidence gets the answer wrong using the potassium argon method, how can we trust it on ancient rocks where we don't have the historical documentation? The answer is we can't. And interestingly, that's also been documented because there were 10 Zairian, that's now the Republic of Congo, diamonds yielded a potassium argon isochron age of 6 billion years, but that means the diamonds were older than the Earth itself. So how could they be older? Well, the answer is the diamonds inherited extra argon. They found that inside the diamond there were fluid bubbles that were rich in argon. And if they didn't take that into account, they got the wrong age. So unless you know the reasons, you can't be sure that you're actually measuring the true amounts that relate to radioactive decay. Let me give you another example from the Grand Canyon, no less, for good reason. It's very in your face when you realise what's going on here. This is a geological diagram of the Grand Canyon. Don't get spooked by the complexity. It's really very simple. See those horizontal layers? They're fossil-bearing sedimentary layers related to the flood. The ones below that are tilted all the way down to the bottom there, bottom left, they're all pre-flood. And in amongst those rocks, near the top of the pile of the pre-flood rocks, just near the beginning of the flood, you've got basalt lavas. I have to keep on reminding myself I'm in Australia, I'm not in the US. Basalt. Cardenas basalt lavas. These are some of the ancient lava flows at the very bottom of the Grand Canyon. But also in the western Grand Canyon, there are still volcanic craters from eruptions that were so recent, the lavas flowed down the walls of the canyon, the Uinkaret Plateau basalt lavas. And we can see the remnants of those lava flows here in the western Grand Canyon. You can see volcans thrown, and you can see where the lavas spill down the walls of the canyon. By the way, you can just see the Colorado River there, and just around the corner is the fastest navigable rapid in North America. Lots of fun. 19 seconds of sheer terror. You want an adrenaline rush, that's the way to get it. So, we've got the contrast between the recent lavas. Some of these lavas erupted at maybe as recently, by the time the Native Americans got to North America, there's some evidence that some of them may have seen some of these eruptions. So we know they're quite young. And these are the ancient, the Cardenas basalt lavas. So just to get the picture, the very ancient ones, the most recent ones. What ages do they give by rubidium strontium? The same rubidium strontium age. The most recent lava flows give essentially the same 1.1 billion year old rubidium strontium age as the oldest lava flows in the Grand Canyon. How can that be? The answer is that they came from the same source, because the basalts actually come from deep at the top of the Earth's mantle. The rocks melt and it comes up through fractures. The most recent ones came from the same source as the ancient ones. In other words, they inherited the same source chemistry. So the chemistry of the rock, of rubidium strontium, has nothing to do with the age of the rock. It has to do with the source of the rock. Isn't that interesting? If you don't take that into account, and there's lots of evidence from recent basalt lavas around the world that the source plays a very important role in determining the chemistry of the rock, and if you don't know that, you'll get vast ages that aren't really true ages. What about contamination? I want to show you a few examples of granites. You all know what a granite is? Well, it's a very coarse crystalline rock, and there's grains in there called zirconium silicates. In fact, they used to mine zircons out here on Stradbroke Island in the beach sands. And these have come from granites. And they've run into a problem when they've tried to date the granites and the zircons in the granites, because they find that the zircon grains are vastly older than the granites. So they assume that the zircon grains have been inherited. So, for example, zircon grains from a Himalayan granite, supposedly 21 million years old, will give uranium-lead ages up to 1,753 million years. Or zircon grains from granites in Australia, southeastern Australia, supposedly 426 million years old, will have zircon grains that give ages of 3,500 million years. That's 3.5 billion years. How could the grains in the rock be so vastly older than the rock itself? And so they say that has to be contamination. Well, hold on. What other contamination is there? It's an arbitrary loophole or escape clause for them to get out from the obvious implications of this. Well, if you think that's bad, here's one example that they can't ignore or get out of. A Himalayan granite, supposedly 20 million years old, has zircon grains within it that have uranium-lead ages up to 1,483 million years, but also contains monazite grains, which is another mineral in there, with uranium-lead ages of minus 97 million years. What does that mean? The grains haven't formed yet. So that's obviously something is wrong with these dating methods if you get such diverse results, assuming that all these minerals formed in the rock at the same time, you get these strange results, tells you there's something wrong with these dating methods. Well, let's go back to the Grand Canyon and let's look again at the Cardenas basalt. Here's the lava flows you can see by looking over into the canyon from one of the eastern Grand Canyon overlooks. And here's the lavas again up close and personal. And here we went in to sample them. And you can see they're the boundary between two lava flows. Now what we did, this was research that we did ourselves in the Grand Canyon on a previously successful research application to the Park Service. We decided we'd do something different. You see, in the textbooks, they claim it doesn't matter which of the radioactive clocks you use, you should get the same result. Well, that makes sense, doesn't it? It's like you've got 4 hourglass clocks lined up on the bench, but they've each got different coloured or different sized sand grains. Okay? So if you start with all the sand grains in the top to begin with, over time the sand grains are still going to fall, and at the end of the day you should have the same age. In other words, the uranium clock, the potassium clock, the rubidium clock, at the beginning, when the rock formed, they started ticking, and they've all ticked through the same real-time period from when the rock formed till when we measure it today. So they should give you the same result. Even though they're different atoms, and they might decay at different rates, they should all measure the same real-time period from when the rock formed to the present day. That's if the assumptions are correct. And that's a big if. So we decided we'd test that, because we couldn't find many examples in the literature where they'd taken the same samples and dated them by all the different methods. So I said, we'll do it and find out if that assumption is correct. And guess what? When we dated the Cardenas basalt, what did we get? The potassium argon gave an age of 516 million years, rubidium strontium an age of 1,111 million years, samarium did 1,588 million years. Which is the correct age? Maybe none of the above. How will we know without an observer? And notice this is not some trivial difference. The rubidium-strontium age is twice the size of the potassium-argon age. The Samarium age is 3 times the size of the potassium-argon. That's not very close to hitting the bullseye, is it? Well, how would you reconcile this disparity? The evolutionists can't, the long-age geologists can't reconcile it, but we can. How? Well, it's simple. If the radioactive clocks were accurate, always ticking at the same rates as measured today, each clock should have given the same age, but they didn't. Therefore, the different ages means that the clocks in the past must have been ticking at different, faster rates than today. What do I mean by that? Well, it's simple. In the Cardenas basalt, the potassium-argon clock ticked through 516 million years from when the rock formed to the present time, while at the same time the rubidium-strontium clock ticked more rapidly through 1,111 million years, and the samarium-neodymium clock ticked even more rapidly through 1,588 million years. Now, remember, those ages are based on assuming the present decay rate. So what I'm saying is we have demonstrated that the decay rates measured today were different in the past. They were faster in the past. And that makes sense because during the flood, you had catastrophic geological processes operating at rates that we can't even imagine or simulate today. So if geological processes of erosion and transportation of sediments and fossilization were occurring catastrophically, why not radioactive decay rates? So the different ages can be explained if these radio clocks ticked at faster rates in the past, at different faster rates than today's measured rates. So that means if the decay rate wasn't constant, radioactive dating cannot yield the claimed absolute ages of millions of years. Now, if you think that this was just a one-off serendipitous discovery, we measured this, we did this repeated on 4 different rock units in the Grand Canyon. I'll give you 2 more examples. This is where the molten basalt didn't make it to the surface out through the volcano. Instead, the molten rock was squeezed laterally between the rocks and cooled under the ground. We call it a diabase sill. And there's several of them in the Grand Canyon, deep in the Grand Canyon. What results did we get? Potassium-argon age of 841.5 million years, rubidium-strontium 1,060 million years, lead 1,250 million years, samarium-neodymium 1,379 million years. Again, which is the correct age. And by the way, notice that the potassium was always younger than the rubidium. That's why he knew there was something systematically going on, because there was the same pattern. Potassium-argon was always the youngest, and potassium-argon was always younger than rubidium-strontium. Here's another example. This is where, deep in the canyon, previous lava flows were metamorphosed by heat and pressure. They were changed into a new type of rock called an amphibolite. And here's the results that we obtained. Again, notice that rubidium is younger than the lead and the samarium. By the way, I should explain, lead is where you contrast, you've got 2 types of uranium decay to 2 types of lead. So you can compare the 2 types of lead to also get an age. And I'll explain later, that's regarded as the gold standard in radioisotope dating, the lead ages. And so we demonstrated that there is good evidence. In fact, there were several, that's just one line of evidence. In that research project, we found that there were 5 lines of evidence that converged on the same conclusion, that decay rates were catastrophically faster in a recent catastrophic event. And that's another story in itself. So how reliable is radioactive dating? We can demonstrate that assumption number 1 is violated by inheritance, assumption number 2 is violated by contamination, and assumption number 3 is violated by accelerated decay rates. But you see, the scientific community simply ignores these problems with these assumptions. You will not find these assumptions discussed in the textbooks. You'll not find them discussed in the scientific papers. They ignore them. Why? Because the millions of years are what they want to obtain. And these methods seem to work for them to give them the millions of years. And they've convinced themselves that they can use the isochron technique because it eliminates the need to know the initial conditions and supposedly indicates contamination when samples do not plot on the isochrons. How does that work? Well, you can take a single sample and you can measure the parent and daughter atoms, and we call that a model age. So you get one sample to calculate the age. The isochron technique takes multiple samples. And it's quite simple. Different samples from the one granite, different samples might have different amounts of potassium in them. Well, if they've got different amounts of potassium, means they'll have different amounts of argon. The one with greater potassium will have a greater amount of argon. The one with lesser amount of potassium will have lesser amount of argon. So when you plot potassium versus argon, the sample should line up on a straight line, the iso, same chron. So you use multiple samples. And that's regarded as the gold standard because it's assumed that if a sample doesn't fall on the line, it's contaminated. But if one sample doesn't fall on the line, maybe it's all the other samples of the contamination. How would you know? And you don't need to know the initial conditions because you're only contrasting the different amounts in the different rocks. So they think they've got around the problem, but they really haven't. They assume the method works because it gives them the ages they want in the right order in the rock layers to so prove the millions of years needed for evolution to occur. But a question I asked myself several years ago, how reliable and objective are the measured decay rates that are used to calculate the great ages? And I'm going to summarise, like I said, in 200 pages of technical literature that I produced as a result of this research. I went back to all the original papers. How are these decay rates measured? There are two parameters. And one of them is the half-life. You've probably heard that, and that's one we'll focus on. Basically, it goes like this. If you start with a pound of uranium, or I should say a kilogram, to translate it into Australian measurements, a kilogram of uranium, in one half-life, half of that uranium will decay to lead, so you have half a kilogram left. And then if you wait another half-life, that half a kilogram will decay to a quarter of a kilogram. And so you get smaller and smaller amounts. There's been three methods used. Direct counting. What does that mean? Well, you stick a Geiger counter in front of a uranium sample. Each click of the Geiger count is a uranium atom that's decayed. So you stick it there for a year, and you can measure 1 million counts in a year. That's 1 million atoms that are decayed in a year, so you know the rate of decay. And then there's the other method, measuring in growth of the daughter isotopes. Instead of having a Geiger counter to measure the uranium, at the end of 1 year, you measure how many lead atoms are in the rock, and that many atoms you'll have assumed have accumulated in that 1 year. So that's the number of uranium atoms that decayed, so you can work out the decay rate. And the third method that they've used is the one based on assuming that no matter what clock you use, you should get the same age. And the interesting thing is, they've often found that you don't quite get the same age. So what do? They adjust one of the decays to get the age to match, and that's how they determine the decay rate. And I'll go into this very quickly. Potassium argon, the potassium-40 half-life. 70 years of determinations. The half-life has been determined at 1.248 billion years. Here's the determinations over the last 70 years. Notice how the earlier results were quite scattered, and they might say, well, that's because the early equipment wasn't very good. Well, the interesting thing is we need to remember that people have more and more relied upon computers rather than being hands-on with their equipment. If you get a computer control what's going on, how do you know, if you haven't got your hands on, whether the experiment is going as well as you think it might be? So in actual fact, some of these early experimenters were probably very good at what they were doing. And notice the red markers, increasingly there's been a reliance on these comparison of ages. Now there's two uncertainties in the potassium-argon half-life. We don't know precisely the abundance of potassium-40 in natural potassium. And not all potassium-40 decays to argon-40. Most of it actually decays to potassium-40. So if you don't know the amount that decays by each way, how can you be sure that you're actually measuring the correct half-life? So the potassium-argon half-life is ultimately being calibrated against standard samples of known lead ages. What does that mean? Well, they dated the same samples with lead and with potassium-argon, and the calculated ages were based on the assumed decay rates. To get the ages to agree, they changed their measurement of the decay rate of potassium so that the potassium age would now agree with the uranium age. Is that objective? No, it's very subjective. You'll often hear them say, oh, but the ages agree. Well, the answer is they've been made to agree by tweaking the decay rate of potassium that they use to calculate those ages. And there's the scientific literature reference there. Don't take my word for it. You can go to that journal and you can read that article for yourself. What about the rubidium? Over the last 60 years, there's been measurements by the various techniques, and the decay rate has been determined at 48.8 billion years. And again, you can see the early measurements were wildly divergent, and then they seemed to converge, particularly as they began to use that tweaking method, tweaking the rubidium half-life so that the ages, the rubidium-strontium ages, agreed with the uranium-lead ages. Well, of course they agree if they're made to agree. But the interesting thing is in the last decade, there's been two groupings of determination results. Group 1 consists of half-lives of rubidium based on measuring Earth materials and meteorites and lunar rocks, and Group 2 only using Earth materials. And so they've found there's this disparity depending on the starting materials that you use. Such groupings can only be sustained if precedence is given to half-life determinations by comparison with the lead ages, in other words, tweaking the rubidium-strontium. The interesting thing is more recent direct counting and in-growth determinations which should be given the emphasis over the other methodology because you're actually directly measuring how many decays of rubidium have occurred, they actually give you an entirely different determination. The actual experiments to measure the actual atoms that decay give you a different result to deliberately tweaking the rubidium half-life to match the uranium, to get the same uranium ages. So, has the rubidium decay half-life been finally determined? No. There's still some uncertainty as to what today's value should be. Ultimately, the rubidium decay half-life is calibrated against lead ages on the same samples. Again, don't take my word for it, it's there in the scientific literature. Samarium, determinations over the last 80 years, a half-life said to be 106 billion years. But again, notice the early ones were all over the place, and then they reached a certain level back in the 1970s in their determination that they decided what the value was. But notice there's two results there that are wildly different. That's interesting. Let me tell you the story. By the mid-70s, comparison of samarium neodymium ages of two meteorites with their lead isochron and model ages had already settled that the samarium half-life was 106 billion years, yet those two more recent direct counting determinations have given higher values and they've been discounted and ignored. These are actual experiments that have been meticulously done. In the 2003 measurement, They used multiple repeated measurements with multiple samarium sources with 2 different counting instruments. And they did a detailed analysis of the efficiencies of their equipment. And yet the scientific community has ignored the results of those measurements, by the experimental measurements, because they disagree with the half-life determination made in the 1970s based on 2 meteorites and their lead, and samarium neodymium ages being made to agree. In other words, there's a lack of objectivity involved here. There was subjective massaging of the results, ignoring the experimental evidence to the contrary. And so the recommended half-life for samarium is now based on the subjective recalibration based on the lead dating of only 2 meteorites. So ultimately, samarium decay half-life is calibrated against the lead ages on the same samples. And again, don't take my word for it, it's documented in the scientific literature. Well, finally, what about uranium? There's 2 types of uranium, 238, 235. 235 is the one that they want for nuclear bombs. And most of your natural uranium is 238. That's why they have to enrich the uranium in 235 to make it for bomb-grade uranium. Determinations over the last 85 years have primarily been by direct counting using the Geiger counter. And there's the currently recommended half-lives. 4.4683 billion years for uranium-238, 203 million years for uranium-235. So there's the determinations over the last 85, 90 years, and here's the 235. But the optimal lead ages still have the effect on them of the crucial uranium-238-235 ratio. What do I mean by that? Remember I said you've got uranium-238 decays to 206 lead, 235 uranium decays to 207 lead. If you're going to make an age based on comparing the leads, you better know what the ratio was between uranium to begin with. Has that ratio been constant? Until recently, it was determined as 137.88. That is 97%, what was the figure I gave you earlier? Just over 99% is natural of uranium is 238. And if you contrast that to the little bit of 235, you get a ratio of 137.88. The interesting thing is that in the last few years, they've been found, as they've done the measurements, great variance in this ratio in meteorites, rocks, minerals, and uranium ores. And if that ratio varies, it requires significant adjustments to the lead ages that are calculated thereby. But the lead ages are the gold standard for calibrating all the other ages. So do we really know those uranium lead ages as accurate as we thought? No, we don't. We've actually found different minerals in the same rock will have different uranium ratios. And it'll vary from rock to rock. Even the same type of granite, the zircons in the granite will give you different uranium-235, 835 ratios. And in meteorites, you get the same variation. So there is still uncertainty about this crucial uranium-235, 238-35 ratio. And these small, consistent differences have been measured in all minerals and rocks. At the same time, there are residual uncertainties about the measurements of the uranium-238 and 235 decay rates. So these 2 problems plague all uranium lead and lead ages. They're all subjected to these large uncertainties. So if there's uncertainties in the gold standard uranium lead and lead ages, that means all the other radioactive half-lives and ages calibrated against uranium and uranium lead and lead ages will never be certain. So that means all radioactive dating is not accurate. So let me conclude this section. Also, let's remember inheritance, contamination, and non-constant decay rates make all the radioactive dating methods totally reliable and unusable. Therefore, the radioactive dating methods cannot provide absolute ages for rocks and meteorites. And don't forget, the age of the Earth was determined on meteorites, assuming an unobserved evolutionary history that is contrary to the explicit statements in God's Word. Well, is there evidence from science that the Earth is young? Yes, but we need to remember that all scientific evidence for the age of the Earth involves unprovable assumptions. We're in the same boat. Why? Because we weren't there when God made the Earth to make measurements. What we do, we take a process and we assume the rate that we measure today has been constant in the past. We have some reasonable and suitable starting conditions, but we cannot prove those conditions because no scientist was there to start to observe them. We assume the process rate has been constant since at the start at the same rate measured today, even though no scientists were there over time to verify this assumption. So all such processes can only ever give a qualitative maximum age for the Earth. Thus, there is no absolute scientific proof of the Earth's age. But surprisingly, most dating methods give a young age for the world. In fact, it's been estimated that 90% of the measurements that have ever been used give a young age. Less than 10% give an old age. Let me just focus quickly on a couple, and there's much more information that you can get in our resources on all of these topics. Let's look at comets. Comets are essentially dirty snowballs. They're made up of dust and ice that orbit through the solar system. But you see, as they get close to the sun, they disintegrate because particles come out of the sun, knock off pieces of ice and dust, which is why you've got the tail of the comet lit up by the sunlight. So they're crumbling, they're disintegrating. Now, everyone says the comets came into existence at the same time as the solar system, and they say that was 5 billion years ago. But these comets are disintegrating so rapidly that in less than 10,000 years there should be none left. So because we still see them today, it means that the solar system is less than 10,000 years old. The Earth has a magnetic field, and it's decaying. It's generated by electric currents inside the Earth's core. The Earth's core is believed to be made up of molten iron with a little bit of nickel in it. And what happens if you get electrical currents flowing through a wire, you can do this in a laboratory, put electrical current down through a wire, you can actually, it generates a magnetic field, which you can measure. Well, that's what's happening inside the Earth. But what we've discovered is that it's decaying away. Why? Because the electrical currents, they bump into atoms and they slow down and the magnetic field gets weaker. We've also discovered there were reversals during the time of the flood. And those reversals will again decrease the stored energy in the Earth's magnetic field. So here's the historical measurements that confirm, this is over the last 200 years, real-time measurements all around the globe indicate that the energy of the Earth's magnetic field has decreased. And we can look at even going back to the magnetic field that's been recorded in pottery that's had magnetic particles baked into with the clay, will give you an idea of the strength in the past and the fluctuations when the Earth's magnetic field changed as a result of the way the currents and things moved inside the Earth during the flood. Now, if we extrapolate that backwards, ignoring the flood, we'd go back over 10,000 years. If you bring the flood in, then you get to a maximum where the Earth's magnetic field would be so strong, it would be as strong as a magnetic star, because it was stronger in the past. You extrapolate backwards. So that limits the maximum age for the Earth's magnetic field, and therefore the Earth at about 10,000 years. Now, you all know that the sea is salty. It's usually assumed that you start with no salt. How long would it take for the salt to accumulate in the ocean to the level at which it is today? Well, we can measure how much salt is coming down in rivers and by other means into the oceans. We can work out how much is going out. Take the element sodium, which is part of common salt, sodium chloride. And starting with fresh water, with the present rate of salt addition, the maximum age for the Earth's oceans is 62 million years. Yet the conventional wisdom says the oceans have been there for 3 billion years. Now let me back up here a minute. Remember I said it depends on your assumptions about the starting conditions? Let's plug in some biblical assumptions here. Would God start with a freshwater ocean? Maybe, maybe not. He certainly made fish to be able to swim in a saltwater ocean, didn't he? So maybe it didn't start fresh to begin with. Assumption number 2. Has the addition of salt always been constant at today's rate? No. With all that erosion during the flood, that releases salt into the oceans today. During the flood, it would have been orders of magnitude greater. In fact, most of the salt would have accumulated during the flood. So that 62 million years comes all the way down. It's a qualitative maximum. And even then, it doesn't agree with their claimed 3 billion year age. Biological materials decay too fast. You've heard the discovery of soft tissue in dinosaur bones, the DNA in Neanderthal, dinosaur blood cells. There's photographs there of the soft tissue and some of those red blood cells. You know, all of those biological materials we know from experimental evidence decay rapidly. The dinosaurs can't be 65 million years old and have fresh tissue in them or DNA or red blood cells because those things can't survive that long. We know that from experimental evidence. In actual fact, fossils do contain radiocarbon. We've tested wood, shells, bones, coal, oil, natural gas. It's all in the literature. We've done our own radiocarbon dating, and all of them contain ages of only thousands of years. That's assuming radiocarbon has built up in the Earth's atmosphere at the rate we measure today. Would have been different in the past because of the Earth's magnetic field. When you start to take into account biblical assumptions, those tens of thousands of years ages crunch down to less than 5,000 years, back to the time of the flood. Even diamonds have young radiocarbon ages. Diamonds that can't be contaminated internally or externally because they're the hardest natural substance that we know. Diamonds that gave ages conventionally of 1 to 3 billion years gave standard radiocarbon ages of about 60,000 years. Once you correct those, they come down to less than 10,000 years. The diamonds supposedly formed at the same time as the Earth formed, therefore the Earth is less than 10,000 years old. And don't you believe what you read in the blogs on the atheist websites, because a lot of what you read on the internet hasn't been peer-reviewed. Some will claim that the diamonds have the carbon-14 because of uranium in the diamonds and underground neutrons. We've done the calculations and demonstrated that it's not possible. The carbon-14 is there because it was there at the time of creation. These diamonds didn't have contact with the atmosphere. The carbon was intrinsic, carbon-14 was intrinsic to when the diamonds were created. And so the carbon-14 dates the formation of the diamonds and therefore the Earth. One last example before we wrap up. You know, the evolutionists claim that there's a Stone Age which lasted for 185,000 years. And through that 185,000 years, the human population was roughly about a constant level of 1 million. You think about it. 1 million people living and dying constantly over 185,000 years. You'd estimate the total population over that 185,000 years would be 8 billion people. Where are all their skeletons? Why do we find so few human remains? Well, we don't find them amongst the fossils from the flood because God said he was going to utterly destroy man from the face of the earth, so he made sure that there were no human fossils with dinosaur fossils that we know of. All the human remains we find at the present Earth's surface, the Neanderthals, the Cro-Magnons, they're all descendants of Noah and his family. And so they're only thousands of years old, which makes sense of only thousands of remains that we've found. By the way, where does the Stone Age fit in? Noah and his family got off the ark. They had an advanced technology that they used to build the ark. They had metal tools that they brought out from the ark. And they went on to build the Tower of Babel. What went wrong? Ken's going to talk about in the next session, there was confusion at Babel. And so those who left hurriedly, left behind their metal tools, what did they get when they got out into the mountains? Picked up stones. They regressed in their technology until they settled in a more settled way of life where they could redevelop their technology that they already knew about to get metals to make metal tools. So it's very simple to understand these things from a biblical perspective. So most methods give a young age, but let's remember all scientific evidence for the age of the earth involves unprovable assumptions, because no human has witnessed all of Earth's history. All scientific methods can only ever give a qualitative maximum age for the earth. But guess what? We actually have the birth certificate for the earth. It's in God's word. The only certainty we have is the God-breathed eyewitness account in the scriptures of the earth's age and history. Here where I leave a challenge. Why does this matter? You see, the tragedy is that so many Christian leaders and Christian scholars have allowed the finite, fallible, fallen human interpretations to trump God's word. You know, they accept the millions of years, but they don't understand that those millions of years are an interpretation based on assumptions that reject the authority of God's word. And then they want to add those millions of years to the Bible and reinterpret the Bible based on determinations that reject God's word. That's a tragedy, because our only certainty is the God-breathed eyewitness account in the scriptures of the earth's origin, age, and history. And in closing, let me remind you why this matters. You see, Jesus said in John 3:12, "I've spoken to you of earthly things and you do not believe. How then will you believe if I speak of heavenly things?" See, Jesus said, if you don't believe what I tell you about Noah and about Adam and about the flood, how are you going to believe that I go to prepare a home for you in heaven, and there will you be with me for eternity? You see, Jesus said, as I mentioned last night, he spoke about the creation which God created, and he said from the beginning of the creation, not after billions of years, God made male and female. And so the evolutionary time frame from the secular viewpoint has the earth coming 4.5 billion years, man coming only in the last million years. And Jesus said, no, from the beginning of creation. The earth was created on day one, man on day 6, 5 days later. That's back at the beginning. Radically different time scale. You cannot reconcile those two. Remember, the Big Bang includes the sun, and they've got the sun before the earth. No, God said, I made the earth first and the sun came later. You see, if we cannot trust Genesis on the young age of the earth, how can we trust God's offer of salvation, John 3:16? Notice that, 4 verses after the verse I just quoted. Jesus said, if you don't believe the earthly things I tell you, how are you going to believe the heavenly? For God so loved the world that he gave his only begotten Son. You see, there can be no compromise with the age of the earth, because the millions of years are based on an assumed, unobserved evolutionary history that is contrary to the explicit statements of God's word. That's why it ultimately matters. That's why I get passionate about that issue, because the millions of years undermine the cross of our Lord Jesus Christ and the gospel message that is the only hope for a dying world that needs a Saviour to rescue it. Well, you've been very patient. Let me just remind you again that you'll get your free digital subscription for 1 year to the magazine. And a lot of this information is already in our Answers magazine, and a lot of the articles are already on our website. And this makes a great gift, by the way, for friends and family. Don't forget the conference special, 15% off. The Answers book, we've even answered radiocarbon in one of these Answers books. And there's DVDs as well. There's only 3 DVDs, but 4 Answers book. There's also this DVD, check it out. These are little 4-minute punchy explanations. There's one on radiometric dating, which very quickly goes through some of the issues that with very detailed little graphics that are very quick-fired, that really help people to grasp these issues. So there's 6 little segments in that DVD that touch on the major issues, including one of those that Ken will deal with in the next hour. The age of the earth, That's not on the table, but it is available. Compromises and crucial assumptions of millions of years. It covers a lot of what I did today. Circular reasoning in the dating methods, that deals with radiocarbon, tree ring dating, and VARV, that is lake sediment dating. And there's also my 2-volume work. It's not 2 books, it's 2 volumes of the 1 book, Earth's Catastrophic Past, and that has all this information in it and more. And then there's our Answers Research Journal. I cannot emphasise enough, it's free. There's no subscriptions required. You just go onto our website, look at the articles, download the PDF files anytime you want to, anywhere around the world. Usually when we have a paper come out, it's featured on the home page on the day in which it's published on our website. So if you regularly get updates from our website, you'll know when there's new papers coming out. And that's where you get all the technical information that underpins the lay presentations of all this information. Well, you've been very patient. Joss, over to you.